Hey guys, happy Thursday. So today we're going to go through Newton's second law and Newton's third law. The first law was that an object in motion is going to stay in motion, an object at rest is going to stay at rest unless we do something to change that. So now when we talk about Newton's second law, we're talking about changing that. So Newton's second law is that a net force, so remember that's just a force that is going to push something or move something in a direction. It's going to cause an object to accelerate in the direction that we applied the force. So if I had like a post and I'm pushing on it this way, the post isn't going to move backwards. It's going to go in the direction that I'm pushing it. And the greater the mass, the greater the force we need to accelerate it. And the greater the net force, the greater the acceleration. So let me put this into like terms that are a little bit easier to understand. So we've got like, think of a T-ball. You've got a baseball sitting on top of a tee. It's not moving. It is at rest, and it's going to stay at rest unless we do something to it. So now here comes Newton's second law. We're swinging a bat, and we're hitting the ball. So we are swinging and hitting, and it's going to move the direction that we applied that force. And if we changed that baseball out for like a bowling ball, we'd have to hit it a whole heck of a lot harder to get it to move. So that's what's saying when we have a bigger mass we're trying to move, you have to use more force. You have to hit harder because that bowling ball is not going to move the same way a baseball will. And the greater the net force, so the harder you hit that ball, the faster it's going to go. So if I just like come up and like barely tap that ball off that tee and kind of almost bunt it, it's going to like fall and roll a little bit. However, if I go through and like Great Bambino swing at it, it's going to go flying and hopefully get a home run. So we're going to use this equation for all of Newton's second law, and it's F equals ma, where our force in newtons, because force is always in newtons, equals our mass in kilograms times our acceleration in meters per second squared. We have to make sure that our mass is in kilograms and our acceleration is meters per second squared because that's how our Newton is. Our Newton is the same thing as kilogram meters per second squared. So we have to make sure that those other two units are those exact same things. So make sure that's written down in your notes. So let's go through this example. You're pushing a friend on a sled and you're pushing them with a force of 40 newtons. Your friend and the sled together have a mass of 80 kilograms. Ignoring friction, so pretending we're on ice, there's nothing that's going to slow the sled down. What is the acceleration of your friend on the sled? So we're going to write down the information that they give us. So our force is 40 newtons, our mass is 80 kilograms, and we're looking for the acceleration. So we're going to use the only equation we have, F equals ma, and they're actually going to go ahead and rearrange this with the letters first. So we're going to divide by our mass to get our acceleration by itself. And so you can also write this equation down in your notes, where acceleration equals force divided by mass. And this works the other way around too. Your mass would equal force divided by acceleration. So if you want to write those other two equations down so they're already done for you, you can go ahead and do that. So from there, we're going to plug our numbers in. And we have 40 over 80, which gives us 0.5 meters per second squared. Okay, so let's talk about weight. Weight is actually the force of gravity on any object. So whatever a scale is telling you how gravity is pulling on you as an object. So because it's a force, the force of gravity pulling us down, we can actually figure it out using this equation. And when we are doing that, our acceleration due to gravity, we use 9.8 meters per second squared. That's a big number. It's going to come in handy. Write that one down, circle it, box it. I've been going through this with my physics students as well. 9.8 meters per second squared, important number. Now, this is not everywhere on Earth. This is actually an average that scientists have calculated because it depends on how far away you are from the Earth's surface. So let's go through this example real fast. We're going to find the weight of a suitcase. It has a mass of 42 kilograms. So I'm going to write down what I know, which is that the mass is 42 kilograms, and I see that it says weight, so I know that my acceleration is 9.8 meters per second squared because that's what Earth does to us. Then I need to find my force, so I use my F equals ma equation, and I just plug my numbers in. So I multiply those two together, and my force, or the weight of that suitcase, is 411.6 newtons. Now there's a difference between weight and mass. So like we were saying, like the friend in the sled weighed 80 kilograms, that suitcase weighed 411 newtons. The mass is how much stuff anything has. So like this pen has so much stuff in it. This calculator has so much stuff in it. We have so much stuff in us. But the weight is how gravity affects that object and all that stuff. So your weight can change based on where you're at. So if you're on the moon, for example, you would only weigh a sixth of what the scale tells you right now. And then if you're on another planet, typically it's going to be a little bit more. So like on Jupiter, you would weigh over twice as much as you do right now. But that doesn't mean that the amount of stuff in any of this has changed. I could take this pen to the moon, and it's still this pen. It still has all that same stuff in it, but it's going to weigh a sixth of what it weighs here on Earth because the gravity isn't pulling it nearly as hard. So let's go to Newton's third law of motion. So Newton's first law, where an object at rest stays at rest and an object in motion stays at motion, that's something that you've probably heard before. Newton's second law is based around that equation, F equals ma. And Newton's third law is another one that you've probably heard, but we're going to go through the science behind it. So every action, let me move myself. Every action has an equal and opposite reaction. So when you have one object exerting a force on another object, we are putting a force on both of those things in equal amounts and in opposite directions. So think about when you're jumping on a trampoline. When you jump up and land on that trampoline, you put a force down on that trampoline. But guess what? That trampoline is pushing you back up with the exact same force. So no matter what, every object is exerting a force on itself. I set this calculator down on a table. The calculator is pushing down on that table with the force. But because that calculator isn't moving, something is equaling that force and pushing back up on it, and that's the table. Every time you sit in a chair, you put a force downwards on that chair. That chair actually is pushing back up on you too. If it didn't, then you would keep pushing downwards and you would fall to the ground. We're going to mostly talk about, though, with this when we're moving. So let's talk about the law of conservation of momentum. Momentum is just when you have an object with mass and it's in motion. And we use the letter P for this for a couple different reasons, mostly because M has already been taken. So the equation P equals mv is what we're going to use for all of our momentum equations. Your P is momentum, and that is measured in kilogram meters per second. This is not the same thing as Newton's. Newton's is kilogram meters per second squared. So we don't have a shorthand for this. You have to write that whole unit out, which means you need to make sure you wrote that down in your notes. Your mass is kilograms, and your velocity is in meters per second. Again, so all of those things match up when it comes to our momentum units. Every single object that is moving has momentum, and it's transferred between objects in a collision. So let's look at, make myself bigger. This is a Newton's cradle. And it's called a Newton's cradle because it really demonstrates all of Newton's laws really well. So if I have one of the balls and I put it in motion, that means it has momentum. But what's happening is that momentum gets transferred into the next ball, and then it keeps going down the line. It gets transferred and transferred until it comes out the other end. And that's really our law of conservation of momentum. So if I put more momentum into this whole system, so let's say I take 2, you're going to see 2 sets also coming out the other end because that's how much momentum we put into it. If I do 3, same thing happens. You have 3 going back and forth. So, what is the momentum of a car with a mass of 1,300 kilograms traveling at a speed of 28 meters per second. So I'm going to write down everything that says. Let's click on the right buttons. I'm looking for my momentum. My mass is 1,300 kilograms, and I'm going at a speed of 28 meters per second. So using P equals mv, I'm going to plug those numbers in, multiply them together, and get that my car has a momentum of 36,400 kilogram meters per second, which is probably a bigger number than you would expect. But think about if a car that's going about 50-ish miles an hour, think about a car going 50 miles an hour, and if it runs into a wall, there's a lot of energy that gets transferred there. So here we have a collision. In a collision, because we have forces that are going onto objects that are equal and opposite, the transfer of the momentum has to be the same. So that's what we're talking about with our Newton's cradle. If I have one going, it transfers momentum, and I have one that ends up on the other side flying out. And if I do two, then two fly out the other side. So I'm always transferring momentum from the start to the finish. It's saved the whole time. So our law of conservation of momentum is that we don't ever create or destroy momentum if we're colliding, but we transfer it. So whatever momentum is going into a collision is also what's coming out of a collision. In this example, ball number 1 is rolling 11 meters per second directly toward a 0.17 kilogram ball at rest. During the collision, ball number 1 stops. Ball number 2 is launched forward at 9 meters per second. What is the mass of ball number 1? So we have a collision, so we know we're going to use our momentum equation. Now, if we're going to think about this, we have ball number 1 rolling toward another ball at rest. During the collision, ball number 1 stops, but the other one moves forward a little bit slower, though. So we're going to write down all the information they give us. Here's a little diagram. So our momentum of ball 1, we don't know. We don't know the mass of ball 1. That's what we're trying to figure out. But our velocity of ball 1 is 11 meters per second. Our momentum of ball 2, we don't know, but we know the mass is 0.17 kilograms and that its velocity is 9 meters per second. Now, because everything that goes into that has to come out, we can set up our equations so that the momentums equal each other. And if they equal each other, then my momentum for ball number 2, which I have all the information for, is my mass times my velocity. It gives me 1.53 kilogram meters per second. And I can set that equal to my mass times velocity of ball 1. Let me actually show you on the board a slightly different way that I can do this. Okay, so I have my momentum 1, I don't know. The mass of 1, I don't know. But my velocity of 1, I know is 11 meters per second. My momentum of 2, I don't know. My mass of 2 is 0.17 kilograms. And my velocity for ball 2 was 9 meters per second. So knowing that my momentums equal each other, P1 equals M1 times V1, and P2 equals M2 times V2. Well, if these guys are the exact same, that means, because of math, that I can just set my M1 V1 equal to M2 V2, because they should equal the exact same number. What they did in their example is they went through a little bit more of what I think is a complicated route. But if you want to go back and look at how they did it, it makes total sense. It's just, I think this is easier to do. So then I'm going to plug in the numbers that I know. So I'm looking for my mass of ball 1, and then my velocity for ball 1 is 11. My mass of ball 2 is 0.17 times my velocity, which was 9. So I'm going to go ahead and do that math. So M1 times 11 equals 1.53. Now I need to solve for M and get it all by itself. So to undo the multiplication, I'm going to divide on both sides. This cancels out. And I take my 1.53 divided by 11. And again, my mass of my first ball is we'll just say 1.4 kilograms. So it's essentially, we're getting the exact same answer. We're just doing it a different way. And I think that way is just a little bit easier to understand. Let me go through this again. Oh, that was the last example. Okay, so make sure you get those notes copied down and then submit a photo of your notes to Google Classroom. Your work for tomorrow is going to be to do a couple of different pages in your packet. I will post those on Classroom today, but they're not due until later on. But if you want to get a head start, feel free. I will be on the Google Meet at 1 if you need any help.